Hello, this time we are going to focus on articles 116, 117, 118, 119, part 1. These are fairly easy because all the principles here are from elementary geometry. And the first theorem is the three internal bisectors of the angles of a triangle are concurrent. They meet in one single point, which we call the incenter of the triangle. In this particular triangle, this is the incircle or the inscribed circle, and I is the center of this circle, and hence we call this the incenter or the incircle. Okay? And then we have the external bisectors of two angles of a triangle are concurrent with one internal bisector of the third angle. Let us extend the lines of this one. So this is the triangle, and I extended the sides of it, and that's the yellow triangle. And then the internal bisectors, these are the internal bisectors, three internal bisectors, and the external bisectors would be these ones, okay? This one bisect this external angle, and then this one is bisecting these two angles, okay? And then this one, this bisects this external angle. So we have three external bisectors and we have three internal bisectors. So the internal bisectors, the first one, there are three internal bisectors and they are concurrent. But the external bisectors, this is the external angle bisector at point A. This is the external angle bisector of point B. And at the same time, this particular angle bisector, the internal angle bisector, these three meet at one single point I sub C. And I think you know why I call it I sub C, because it's opposite vertex C. And that's I sub B contains this external angle bisector, this internal angle bisector, and this external bisector of angle A. Last but not the least, I sub A contains three lines: the external angle bisector of point B, the external angle bisector of point C, and the internal angle bisector of point A. Hence, the theorem, the external angle bisectors, etc., etc. Okay, let's try to remove first the extended lines, and then the what's the thing that we need? The internal bisector and the external bisectors. Okay, if you notice, people, since these are external angle bisectors, I'm sure you know that there will be three more circles involved in it, and these are what we call the X circles associated with these triangles. Okay, and that's the main idea behind this particular section of the textbook. Okay, but let us hide one more time the circles as well as the extended lines. So let's try to prove each one first, okay? So maybe what we need to do is recall this basic theorem that we learned a long time ago, that if a point lies on the bisector of an angle, then that particular point is equidistant from the sides of the angle. What that means is this point P lies on the bisector of angle B. That means angle 1 is congruent to angle 2. And I want to know the distances from P to X, and that's a perpendicular distance. The P to Y, those are the two perpendicular distances. What it says here is the fact that they are equidistant, meaning to say I need to show that Px is equal to Py. I don't think that's very difficult because angle 1 is congruent to angle 2 because the angle is bisected, and BP is congruent to itself, and this has to be right and this has to be right, and therefore by AAS principle, then the two triangles are congruent, And since the two triangles are congruent, we can easily claim that px is equal to py. And the converse of that particular theorem is that if a point is equidistant from the sides of an angle, that means if px is equal to py, then it has to be on the angle bisector. So if px is equal to py, then can we show that they are congruent, the two triangles? This is congruent to this, and then this is congruent to itself. This is congruent to this one because that's right angle, and therefore that is HL theorem, hypotenuse leg theorem, tells us that the two triangles are congruent, and therefore angle 1 is congruent to angle 2, and therefore P must lie on the angle bisector. So what we say is that every time a point is on the angle bisector, it is equidistant from the sides. So let us prove this theorem, okay? The three internal bisectors are concurrent. So what we'll do is we'll assume first, so we want to know whether these 3 points will actually meet in one single point. So two lines will always be intersecting. So this angle bisector and this angle bisector, let us assume that they meet at point I. So all that we need to do is to focus on the angle bisector of angle A. So since BI and CI are angle bisectors, then first we consider this one. I being the angle in the angle bisector of angle B means that IX is equal to IC. I being in the angle bisector of angle C means that IX is equal to IY. Hence we have this result, okay? And therefore, Ix equals IC, Ix equals Iy. We have no choice but to consider, but to claim that Iy is equal to Ic. Okay? However, since Iy is equal to Ic, let us look at Iy is equal to Ic, but these are the sides of angle A. And since these are the sides of angle A, we have no choice but to claim that point I is also equidistant from the sides of angle A. That's the converse of the theorem, okay? And that's it. So, that means we finished the theorem. That's how easy it is, okay? Then, we have the other things that we need to do. So, just terminologies, okay? The blue circles are the X circles, okay? And then the center points are the X centers, etc., etc. And then we must realize that this radii, this must be congruent to each other, and those are at the point of tangency. And then this is the second set of radii. The next set of radii come from this circle, and finally, the third set of circles are coming from that one. So, the first corollary is from Article 119, and it says that the four tritangent centers lie on 6 lines. Where are the 6 lines here? Let's consider the 3 external bisectors. Let me hide this, hide this, and hide this. Okay? The 3 external bisectors and the 3 internal bisectors. Okay. The 4 tritangent circles lie on 6 lines. Okay? T sub A, T sub B. So this is T sub B. This is T sub A, and this is T sub C. The external bisector is now T sub B prime. This external bisector is T sub C prime, and this external bisector is T sub A prime. And that's the thing that we've got. Or we can phrase it in another way, that each tritangent center lies on 3 lines, and each line lies on 2 tritangent centers. Okay? The second corollary is best discussed after Article 122. So I would like to postpone the discussion of this one because right now it's not so obvious. So it is possible that Mr. Court meant it to put it after Article 122 and not here. Okay? And that's all, folks. I'll see you in the next article, in the next discussion of the article. Thank you very much. Bye bye.